Today we are going to start a new chapter, algebraic structures. For today's session, we will discuss some of the topics: binary operation, algebraic structure, semi-group, monoid, group, and abelian group. First, let us discuss what is a binary operation on a set. Let G be a non-empty set. Let G cross G. We all know that it is a Cartesian product in which it is set of all AB such that both A and B belongs to G. Now if f it is a function from G cross G to G, that means the domain is G cross G and the codomain is G. Now if it is a function, then it is said to be a binary operation on the set G. For example, if star is a binary operation on G, then for every A and B belongs to G, A star B also belongs to G. In other words, A star B is also called closure property. That is, G is closed with the operation star. For example, let us take 3 and 5. Both belongs to a set of natural numbers, that is n. Now, their addition, 3 plus 5, that is 8, that is also belongs to n. So we can say that plus, the operator plus is also a binary operation for the given set n. Let us take another example. 7 and 10 both belongs to n. Now 7 minus 10, that is minus 3, that does not belongs to n. So what we can say is minus, that is not a binary operation for the specific given set n. Similarly, division is also not a binary operation for the above example, as 7 divided by 10, that would be not a natural number, so it is not a binary operation. Next one, that is composition table. Let S be a finite set consisting of n elements. Then a composition star in S can be described by the table. For example, here star is the operator and we have three elements A, B, C. So we can draw a table like this. Here in this entry, AA, that is A star A and B, that means first row and second column, that is A star B, and similarly we can put all the entries. For example, we have a set 1 minus 1 I and minus I. Then the table will contain 4 rows and 4 columns. See here 1 and 1 entry, and here the operator is multiplication. So 1 into 1 1, 1 into minus 1 minus 1, 1 into I, that is I, 1 into minus I, that is minus I. Now same way, see here I and I, we know that I into I is I square, that is minus 1, so here it is entry minus 1. Similarly, minus I into minus I, minus I into minus I is minus of minus, that is I square, that is minus 1. Same way, minus I into I, that is minus I square, and I square is minus 1, so the entry is 1. For example, this is the question: is addition a binary operation on the set minus 1, 0, and 1? Here, the operator is plus, and we have three entries. Now, see, minus 1 plus minus 1, that is minus 2. Same way, minus 1 plus 0, minus 1 plus 1, that is 0. And same way, we can put all the entries. Now, see that here, minus 2. Here, minus 2, that does not belong to the given set. Same way, 2, that does not belong to the given set. So here addition is not a binary operation for the specific given set. Okay, now algebraic structure. A non-empty set G equipped with one or more binary operation is called an algebraic structure. If star is a binary operation on G, then the notation G star is an algebraic structure. For example, n plus, that means set of natural numbers, and the operator addition, that is a binary operation and the whole combined n plus is called an algebraic structure. Same way n into multiplication, uh, I, that is set of integers, and addition I and multiplication R and multiplication. These are the examples of algebraic structures. Now next, properties of binary relations, or sorry, binary operations. Now first one, closure. Now if for every AB belongs to G, if A star B also belongs to G, then we can say that G is closed under the operation star. Now the second property, associativity or associative property. For every ABC belongs to G, if for every ABC belongs to G, if A star bracket of B star C is same as bracket of A star B star C. For example, we can take three numbers 2, 3, 5 that belongs to integers now, and we are defining plus as an operator. Then 2, it is obvious that 2 plus bracket of 3 plus 5 is same as bracket of 2 plus 3 plus 5, and it is also same in the multiplication. So hence we can say that addition and multiplication both are associative. The third, commutative. That is, if for every A and B belongs to G, if A star B is same as B star A, that means we can change the order. Then star is called a commutative. Next one is identity. There exists an element E belongs to G such that A star A is itself A, or and that is same as E star A. Then the element E is called an identity. Fifth one, inverse. That means there should be an element B in G such that uh, such that A star B equals to identity, that is E is same as B star A. Now groupoid definition. A non-empty set G with binary operation star is called groupoid if the binary operation star satisfies the closure property. Only closure property. If it is only closure property is there, then it is said to be a groupoid. Next one, semigroup. A non-empty set G with the binary operation star is called a semigroup if the binary operation satisfies the following properties. The first one is closure, and the second one is associative or associativity. Next definition, monoid. A non-empty set G with binary operation star is called monoid if it satisfies the following properties. Now, the first one, closure, second, associative, and third one is added, existence of identity. So here there are three properties, closure, associative, and existence of identity. Next, group. This one is important. A non-empty set G with binary operation star is called group if the binary operation satisfies the following conditions. The first is closure, the second one is associative, the third one is existence of identity, and again one property is added, the fourth one, existence of inverse. Okay, so if it satisfies all these properties, then we can say that it is a group. Closure, associative, existence of identity, and existence of inverse. Next, Abelian group or commutative group. Now, a group with commutative property is known as an abelian group. That means first of all it has to be a group with commutative property. So that means it should follow how many properties? I think 5. The first one, closure, the second one, associative, the third one, existence of identity, fourth one, existence of inverse. These all are properties of group plus commutative property. That means fifth one, commutative. Okay, so let us consider the graph. Now see here, if it is algebraic structure, then it should satisfy this property, closure one. Now semi-group, that means it should satisfy closure plus associative. For example, group, then it should satisfy closure, associative, identity plus inverse. And for abelian group, it should satisfy all the 5 conditions. That means closure, associative, identity, inverse, and commutativity. Okay. Now we'll discuss 2 or 3 examples, then we'll stop. The first one. Here the question. Let Q plus be the set of all positive rational numbers and star. It is a binary operation defined as A star B. Here A star B is defined as A into B by 3 and show that it is an abelian group. Okay, now to prove or to check whether it is an abelian group, all we need to do means all we need to check are all those 5 conditions or all those 5 properties. Now the first one, closure. Now in every most of the examples, closure property is very obvious. First one. Now for every AB belongs to Q. See, if A and B belongs to Q plus, then A star B, that is defined as AB by 3. Now A star B equals to AB by 3. If both belongs to Q plus, then AB by 3, that is also belongs to Q plus because they are positive rational numbers. So it is obvious. So we can say that Q plus is closed under star. Hence the closure is proved. Second one, associative. For every ABC belongs to Q plus. Now all we need to check those 2 conditions. The first, A star bracket of B star C, that is A star. Now first calculate bracket of B star C. Now A star B is defined as their multiplication divided by 3. So here B star C is defined as BC, B into C by 3. Now consider this as a whole element. Then A star BC by 3. What we'll get? That is ABC by 9. Same way, bracket of A star B star C. That is AB by 3 star C. Again, consider this as a whole element. Then we'll get ABC by 9. So we can easily check that both are same. So that is A star bracket of B star C is same as bracket of A star B star C. Hence it is associative. The third one, existence of identity. For every A belongs to Q plus, there exists some element. Here that some element is 3 belongs to Q plus such that here A star 3, that means A into 3 divided by 3, and that is A. So here A star 3, that means there is one element such that if we multiply A and 3 and the division by 3, then we will get A itself. The next 3 star A equals to 3 into A divided by 3, and that is A. So that is identity is obvious. Hence 3 is the identity element for star, and also 3 belongs to Q plus. Next, existence of inverse. Here for every A in Q plus, there exists B belongs to Q plus such that A star B equals to identity. That means here A star B equals to 3. That means there exists some B such that A star B equals to 3. Now we need to find B. So A star B is AB by 3, that is equals to 3. Now we can calculate B, and that is B equals to 9 by A. That will also be in Q plus. So hence inverses exist. Okay, next one, commutative. That is also obvious. For every AB belongs to Q plus, A star B, that is A into B by 3, we can write as B into A by 3, and that is B star A. Hence it is commutative. Here all the properties are satisfied. So Q plus star is an abelian group. Okay, now next example. Let Q1 be the set of all rational numbers other than 1, except 1, and star is a binary operation on Q1 and defined as A star B equals to A plus B minus AB. That means their addition minus their multiplication. Show that it is an abelian group. Now again we need to check those 5 conditions. The first one is closure. That will be very obvious. Now for every AB belongs to Q1, then A star B, that is A plus B, their addition minus their multiplication, that is also belongs to Q1. Okay, so closure is there. The second one, associative. Here for every ABC we need to take 3 elements. For every ABC belongs to Q1, A star bracket of B star C equals to. Now A star. Now first calculate B star C. Here B star C is defined as their addition minus their multiplication. That is B plus C minus BC. Now consider this as a whole element. Now A star, this whole element, that is equals to A plus that element minus A into that element, and that will be A plus B plus C minus AB minus BC minus AC plus ABC. In same manner, we can calculate bracket of A star B star C, and that would also be same. So hence it is associative. The third property, that is existence of identity. Here, for every A belongs to Q1, there exists some E, some identity element such that A star E has to be A itself. Okay, but here also we have a condition that AE is not equals to 1. Okay, now A star E is defined as A plus E minus A into E. That means their multiplication, sorry, their addition minus their multiplication equals to A. A and A will get cancelled. Now we can common E, that is E into 1 minus A equals to 0. So hence E has to be 0. Uh, here E into 1 minus A equals to 0. That means someone or some number has to be 0. So that means E equals to 0, as it cannot be, A cannot be 1. Okay. Now next. So that is A star 0 equals to A, and in similar manner 0 and star A both are same. Fourth, existence of inverse. Here, for every A belongs to Q plus, there should be some element B such that A star B equals to the identity. Here, the identity is 0. That means A star B equals to 0. Now we need to calculate B. So A star B is defined as A plus B minus AB, and that is 0. Now take B common, so A plus B equals to 1 minus A. Okay, then B equals to A upon A minus 1, and that is also belongs to Q plus. You can check it. Hence inverse is also there. And the fifth one, commutativity. Now for every, this one is also obvious, for every AB belongs to Q plus, A star B equals to A plus B minus AB, that we can write as B plus A minus BA, and that is B star A. Hence it is commutative, hence it is an abelian group. Okay, the last example. Yeah, this one is interesting. Here, let R is given 0 degree, 60 degree, 120, 180, 240 and 300, and A star B is defined as overall angular rotation corresponding to successive rotation by A and then by B. Okay, so for this 6 elements, first we need to find that composition table. So the table will be like this, and the question is show that R star is a group. So here we need to check only for a group. So that means we need to check only 4 conditions except commutativity. Okay, the table will be like this. Here all the 6 elements, or here all the 6 elements, and the operation is star. Now how it is defined as, now 0 plus 0, that is 0. Now 0 plus 60 is 0. 0 plus 120, 120. So this first row and first column will be easy. Now 60 plus 60, that is 120. Now 60 plus 120, 180. 60 plus 180, 240. 60 plus 240, 300. Now 60 plus 300, that is 360, but it is same as 0 degree. Okay, now next 120 plus 0, 120. Up to this it is easy. Now 120 plus 180, that is 300. Now 120 plus 240, that is 360, and that is 0 degree. Now 120 plus 300, and that is 420, but it is same as 60 degree. Why we are doing this? Because we need to check whether it is a group, so the closure has to be there. So that means each and every element should belong to the given set. Okay, now if we write here 360, but that is not in the set, so 360 is same as 0 degree. Now here 180, same way 180 plus 0, 180, 180 plus 60, 240, 180 plus 120, 300, 180 plus 180, 360, and that is 0. Now 180 plus 240 is 60, 180 plus 300, that is 480, and it is same as 20. So in similar manner, we can calculate all this. Now first, the closure property. It is obvious from the table. Now take one example, A and B. For example, take A equals to 60 and B equals to 180. Then there is star, that is 240, that is also belongs to R, and you can check that all the numbers, all these entries will be in R. So closure is there. The second one, associative. Now for every ABC belongs to R, this one is also obvious. What we need to check, A star bracket of B star C is same as bracket of A star B star C. Now let us take one example, 60, 120 and 180 degree. Then A star B star C. Now B star C, that is 120 star 180, that is 300. Now 60 star 300, that is their addition, that is 360, but it is same as 0 degree. In same manner you can calculate this one, and that will be also 0 degree, hence it is associative, and no need to check for all the entries, that would be very longer. Third, existence of identity. For every A belongs to R, here what will be the identity? 0 degree will be the identity, such that A star 0 degree is A itself. Next, existence of inverse. Now here, for every A belongs to R, there exists B, such that A star B equals to identity, but here identity is 0, so it is 0 degree. For example, from the table, what will be the inverse of 0? That is 0, that is obvious. Now inverse of 60, so that means 60 into some element that will give 0 degree. So that element will be 300, because 60 star 300 is 360, and that is same as 0 degree. Now inverse of 120. Now 120 plus something, that will give 360 or 0 degree. So here 120 degree star 240 is same as 360, and that is 0 degree. So it will be very easy to understand. So hence R star is a group. Here it is we need to check only for group, so only 4 conditions are there. Okay, thank you very much.